Welcome. Thank you all for joining us today for this webinar on securing eBPF with Runtime Integrity. My name is Jamie Gassman. I'm Principal Product Strategist here at Invary. And here at Invary, we ensure the security and confidentiality of systems by verifying their runtime integrity with NSA licensed technology, and we enable organizations to uncover hidden threats and reinforce confidence in their existing security posture. Our session today centers on the eBPF subsystem, and we'll explore example APTs and discuss how they work and how Invary's runtime integrity approach mitigates those threats. We're also planning an upcoming webinar I'd like to put on your radar, where we'll take a deeper dive into the eBPF ecosystem with panelists from the NSA and from industry. So keep an eye out on that, and we'll definitely send you personalized invitations. As a reminder for how we'd like to conduct the session today, if you have questions, please look at the bottom of your screen and find the Q&A function of the webinar. Post your question there. We'd love to continue to incorporate those questions as we go. The panelists are pretty good about that, but if we don't get to your question during the presentation and this demonstration period, we will definitely get to them afterwards in the Q&A session, or if they're more specific to you, even follow up on email. So I'd like to introduce our panelists today. With me are Jason Rogers, Scott Furman, and Steve Perry from the Invary team. Jason, would you like to start and introduce yourself?
Sure. Thanks, Jamie. Hi, everybody. I'm Jason Rogers. I'm the CEO of Invary. I'll be one of the folks taking you through one of our demonstrations today.
Great. And Steve?
Hi, I'm Steve Perry. I'm a principal architect working on the eBPF solution here at Invary.
And
hi,
Scott?
everyone. Yeah, I bring a technical background in designing, architecting, and delivering technology and security solutions, including data center infrastructure, cybersecurity, cloud, and other programs. And I've been a technical contributor and executive in startups, government, managed service providers, and growth companies like TierPoint and High Velocity.
Wonderful. Scott, I'll leave it to you, and you can get us kicked off today. Thanks.
Great. Let me share my screen here. Well, I appreciate everybody's time today. We'll get started here. Just a quick background on Invary. So Invary was started through a collaboration between government and research, the NSA's Laboratory for Advanced Cybersecurity Research and University of Kansas. And one of Invary's founders is Dr. Perry Alexander, who spent his career researching trusted mechanisms and collaborating with DARPA and the NSA for decades. And through this collaboration, the NSA developed and used an appraisal technology that helps validate and prove that systems have integrity. And so as they did that, ultimately the NSA decided to declassify the technology, and Invary was created to optimize and bring this technology to the commercial market, really to help secure organizations and protect our national security with the evolving threats that have existed and exist today. And so Invary initially focused on comprehensive and continuous kernel runtime integrity for Linux and Windows. And now, through this ongoing research collaboration with the NSA, we have released Invary's eBPF integrity, which is the focus of today's discussion. And so from an agenda perspective, today we'll be covering a quick recap of eBPF, review how eBPF provides safety and security natively, and then review integrity measurement and why that's critical for eBPF, and then get into some really great, interesting demonstration of attacking eBPF during runtime to kind of back up what we're saying. So Extended Berkeley Packet Filter, eBPF, was added to Linux, the Linux kernel about 11 years ago to enhance the classic Berkeley Packet Filter, which primarily was used for packet filtering functionality like TCP dump. eBPF, as we have it today, has seen significant improvements over the years and primarily enables the four areas shown here. And I like to describe eBPF as kind of extending the operating system kernel capabilities through application development in a privileged context, with two kind of incredible benefits to developers. One is not having to wait for long submission, review, approval, and release process to the Linux kernel source code. and to having to load kernel modules. And by kind of avoiding those things, this is, eBPF has enabled, development speed and innovative use. And so, how is eBPF being utilized today and by who? Here you can see a very, very small sampling of organizations using eBPF, but many popular security products that organizations rely on to protect their systems are actually using eBPF. A few additional highlights of eBPF use not shown here that I just kind of wanted to highlight and call out is like Meta's use for load balancing. Cloudflare uses it for load balancing, but also for DDoS protection and security enforcement. Netflix uses it for fleet-wide network observability and performance monitoring. Walmart for load balancing. And LinkedIn also uses it to improve their direct observability of the server infrastructure that they have. So a few examples there. But it's ultimately safe to say that many organizations with large infrastructure and service deployments on Linux, containers, Kubernetes are probably utilizing eBPF today. And they really are trusting eBPF with critical services. And really that extends to an internet-sized user base. So with that trust, let's transition to kind of the main native safety and security mechanisms that exist in eBPF. And with that, Steve, maybe you can chime in here and highlight and comment on some of these items here shown for our guests.
Sure. BPF it provides a sandbox within the kernel to run privileged code. And so it has a lot of protections in place to keep the kernel sound and to make sure that BPF programs aren't impacting performance or safety, memory, safety, reliability, et cetera. So it does verification at load time by inspecting the raw BPF instructions. After translating them and doing all the relocations, it runs it through static analysis. And that allows it to do things like verify that you're not going to have a kernel panic, that it's not going to cause a kernel panic, that it's not going to allocate memory beyond where it's supposed to, that it will free memory, etc. It also provides a restricted set of calls into the kernel by way of BPF helper functions and kfuncs. And so it doesn't allow access to the entire internal kernel API for the programs. It makes it go through safe places. However, some of those can do some pretty astonishingly powerful things. So also it's restricted by capabilities in the Linux system. So you have to have cat BPF or cat sysadmin in most cases. And so they've done a lot to try to make sure that your BPF programs are safe and can't disrupt the operating system, can only be loaded by folks with privileges.
And Steve, maybe it's a good point too to talk about the differences between eBPF on Linux and on Windows. It's such a powerful, safe extension mechanism on Linux. What's it like on the Windows environment?
Sure. So on Linux, it's very full-featured. As Scott said, BPF itself has been around for a long time, and eBPF, the really greatly enhanced version of the same thing, is at least a decade old and in really heavy use. It's a bit newer on the Windows side. Just in the last couple of years, they've started porting it to Windows. At the current time, Windows eBPF functionalities mostly limited to the network-related eBPF program types. And so there are some quite a lot of differences in terms of the capabilities. In the future, I'm personally hoping that Windows expands into some of the observability and other functions. There are a few differences too on the Windows side with respect to how BPF programs are loaded and how the JIT works. It gets pretty deep and obscure, but the Microsoft implementation essentially treats BPF programs as special cases of drivers. So, yeah.
Excellent. I appreciate that explanation. I'm sure many of our guests today have a pretty good foundation on eBPF and that. So maybe next, Steve, kind of walk us through like how a malicious actor might view eBPF as an attack surface?
So it's an intriguing target for advanced actors because it is running in the kernel and has super low level access. Unless an organization is used to really monitoring and inspecting their systems and infrastructure's use of eBPF, it's pretty hard to see what's going on down at that layer. So it has a lot of capabilities, and it is also a decent place to hide. Um, there are some ways to look at the attack surface of eBPF. One of them is in the fact that programs are really only checked for safety and validity at load time. And after that, they're simply either running in interpreted mode in the kernel's VM, or they've been JITted and are running directly as native code as part of the kernel. So there are ways that an attacker can manipulate eBPF if they do some temporary permissions or privilege escalation. And once they've done that, it's kind of, there's not a lot of super fine-grained privileges around eBPF, so they can do a lot of different things there. We're going to show some of those in our demonstrations in a little bit here.
Great. And maybe another note too, right, is just commenting on the fact that like eBPF largely is available upon installation, right? Like it's activated and there. It's not something that has to be enabled, right?
Right. Yeah. Most Linux distributions ship with eBPF enabled, and in fact, more of them, especially those that use systemd, already have eBPF programs running out of the box when you start the operating system, because they're being used for things like built-in classifying schedulers for packet handling and other things. So oftentimes when you start up a new Linux distro, you can see eBPF programs running that come with that distro.
Yeah, I'm sure in some cases there might be things running that people don't even realize are actually running, right? Or could be in that. So great, appreciate that. Maybe next, so with that context, like how does then our technology help add, additional and needed protection to the eBPF at runtime?
Go ahead, Steve.
Yeah. So essentially, we want to guarantee the integrity of your eBPF programs. So if you've loaded an eBPF program that you know and trust, our solution guarantees that that program is not tampered with or manipulated at runtime. And so that's really pretty important. We're going to demonstrate what happens if you don't guarantee that, and what an attacker might be able to do with that capability. We do a bit of additional work in terms of checking signatures and hashes of the eBPF instructions, both at load time and then also again at runtime, to be able to give you some additional information in addition to the core integrity guarantees that we provide.
And I think just to add on there too, Steve, with the Invary solution, we start with verification of the kernel. So we're asking the kernel some information to do this runtime verification of the eBPF space, but we already know that kernel has integrity when we make those asks. So kind of building from the core up, and this sort of runtime validation space is super important. And runtime, we say it a lot. The last slide, pointed out that really the core eBPF subsystem is only verifying those loaded bits at load time, right? So after that, it's like, I'm sure it's fine. So quite a necessary piece to add to the puzzle, as you'll see here in a second.
Right, and as part of the verification of the kernel, we verify all the pieces of the eBPF subsystem itself, the virtual machine, the loader, the JITted instruction set part, the eBPF file system that is loaded to keep track of these programs and their maps and the data. So we make sure that none of those foundational infrastructure pieces of the eBPF system in the kernel have been tampered with before we even begin verifying the integrity of the eBPF programs you've loaded.
Absolutely. And to tease the next webinar a little bit, the NSA partners that we perform research with have open sourced a new library that they call SEABE, SEABEE, available on their GitHub already. And we'll have them actually walk through it in more detail, but it is an additional hardening tool for boot load time of the subsystem. So the combination of Invary validating the kernel and then the eBPF programs at runtime with this open source project of hardening of eBPF adds even a greater layer of protection. So super excited to have that team walk us through that here in a few more weeks too.
Great. No, I appreciate that context, and I think now we'll jump into the fun stuff. Again, if you have any questions as we go here, pop them into the Q&A, and happy to answer them as we go along here. But I'm going to go ahead and turn the control over here to Jason and Steve to show us some attacks against eBPF and what that might look like.
Awesome, Scott. Thanks. All right, we're going to do 2 demos today, which is always dangerous to do one. So we're going to try to do 2. Hopefully they go well. So this first demonstration we're going to walk through focuses around how an EDR, a common EDR, might use eBPF, how an attacker might then attack that functionality at the eBPF layer. And then we'll show here a little bit about how Invary is catching those APTs behind the scenes. So Steve has put a lot of work into these compromises and some of these demonstrations as well. So I'll ping him here in a little bit when we actually come and talk about the attack. A lot going on the screen here. So very, very fun set of terminals. Just to explain it a little bit, this top right panel is a view of Invary running in the background. So in the background, we're appraising both the kernel and the eBPF layer on this particular system about every minute, maybe a little bit faster than that. Checking all kinds of things. There's past webinars where we go in depth about the kernel, but really making a strong statement about the integrity of the system. Currently showing that both the kernel and the loaded eBPF programs have integrity. This left-hand box is a simulation of a common EDR. So all of the brand names that you would recognize, from CrowdStrike to SentinelOne to Defender, whatever, running on Linux, almost always are using eBPF to drive their functions. They're using it in ways to say, hey, when these events happen, let me know about it. Tell me about what happened in those things so I can inspect it, make sure things are the way they're supposed to be. Steve, do you have additional thoughts into how EDRs are using eBPF that we want to dig into?
I mean, they're using it to watch all kinds of things, what tasks and processes are launched, changes to file systems, events like execution of sudo for privilege escalation. They track a huge number of things and then perform some analysis on the agent itself sometimes, and then forward a lot of the rest to the SIEM or to their cloud platform to do even deeper analysis. But yeah, they monitor quite a huge amount of activity on the machine, in addition to actually running some security logic on the box itself.
Yeah, absolutely. And I think it was Scott mentioned it earlier that we also, maybe you mentioned it, Steve, we provide some insight into what is running in your eBPF subsystem on your boxes. And it turns out most people don't know. And then once you realize what is there, there is a lot going on. Especially if you have a sophisticated system running endpoint protection, running DNS, traffic filtering, traffic routing. So Steve will share some of that as well when he goes into his attack. But our sample EDR, we're going to use the use case of looking for file permissions. So it has an eBPF program already loaded that is watching the system for a change in file permissions. And then this little guy right here is our attacker, and I'll do some things here in a second. And then down here is the kernel log, and we're actually going to get to see what happens in the system to some extent when the attacker deploys their APT. and what happens to the eBPF layer in there. All right, so the first thing, just to prove that we're alive, is I'm just going to change file permission on a file called test file. And what should happen here, our eBPF program that's running from our EDR should pick this up, say, hey, I noticed this happened. It might be an info level event back to a SIM, something like that. So sure enough, changed file permission. It picked it up and said, hey, it's changed with this command, with this process. Pretty typical EDR stuff. And you can imagine your EDR doing this in spades across the system. So now, as the bad guy, I actually want to not have that happen. I want to change some file permissions. I actually know that the system is running this particular flavor of EDR. I understand it's eBPF program. I've seen them before. So I'm actually going to attack it. And I'll have Steve talk about this attack here in just a second. And kind of what we saw down here in the message log. But once I've attacked the eBPF space of the EDR, I'm now able to change file permissions, if I can spell the name correctly, without our EDR picking it up. You'll notice here that actually Invary just picked up that the running eBPF program for my EDR is now failing integrity. We'll talk about that more in a second, but let's take a step back and Steve, take us through that attack that flew through as a shell script that we just ran, but what's it actually doing?
Sure. So in this case, the BPF program itself is it's a trace point that's watching a system call for chmod. And the attack understands that this is a trace point program and that it's going to execute every time the low-level system event happens for the syscall. And it knows that that program needs to capture that event, grab some additional information about the process, etc., and send that back to the EDR agent running in user space. And it does that through eBPF maps. So this particular, and that's the way most of the eBPF observability stuff that's used in EDR agents works. So this particular attack finds the memory location of that JIT compiled BPF program running in memory in the kernel as an attachment or an addition to the kernel. It then looks at the instructions and it rewrites the instructions directly, dynamically by manipulating kernel memory so that the program no longer sends that event back to user space. And so the outcome is that the EDR agent is still running. The eBPF program that it thinks is feeding it information is still running, but it is not communicating events between the kernel and the EDR system. So effectively, the behavior is hidden. Sorry, Jason, go ahead.
No, that's okay. I didn't mean to interrupt you, but something you just said is really important there. I might be monitoring my EDR system either as the vendor or as the user, and to me, it's running. All the eBPF programs are loaded. I think it's fine, right? I don't see anything wrong from the outside. And also the eBPF subsystem was like, this is great. It's an eBPF program. You can change it. So the controls that were in place at load time aren't really there at runtime, allowing sort of the attacker to do that. But super important to know that this is a way that somebody can get in and disrupt that activity, but yet from your perspective, it looks like everything should be working. So a bit of a dangerous situation, I think. From that, Steve, anything else on the attack or we'll reverse it here in a second. So maybe there'll be some more pieces there, but anything else to add?
No, I mean, other than that, EDR agents often have their own sort of anti-tamper logic, and this technique makes it past a lot of that because, again, the eBPF system's happy, the eBPF program's running. So, yeah.
Absolutely. And just to talk a little bit about Invary again, on the upper right-hand side, you'll see here for our eBPF monitor category of integrity, it is failing. So obviously it picked up that the eBPF program attached to the EDR has changed. And in fact, identifying exactly where that program was changed and what it was changed to. So not only are we able to identify this has happened, but we're able to identify the exact place that it happened by verifying its integrity. Now, as the attacker, let's say I'm done and I've done whatever bad thing I want to do. I want to back myself out of this. Can actually then go back and restore that eBPF program to what it was. Again, no one the wiser, not being picked up really anywhere else in any kind of monitoring or logging that's going on. And I can repeat my test again, and all of a sudden I'm working again. So again, to you as the operator, you think everything's working. Or before, it works now, everything's running. But I was able to get in there in the middle. And for those of you who haven't seen the kernel APTs that we've also done a webinar on, it shows you that once I'm in, I can also obfuscate these logs that we're showing around too, right? So I can completely hide the fact that I'm in there doing anything from a log perspective to the eBPF layer. Obviously, Invary now also knows that we retain the history. It failed during those few minutes that I was attacking the system, but now that it's restored, we've gone back to a state of full integrity in the system. Great. Any other comments, Steve, before I hand it over to you when we go through more of a network observability attack?
Nope.
Awesome. I'm going to stop sharing and hand it over to you then.
Okay. So there's a little bit more going on with this demonstration. Unfortunately, it's more windows. But this demonstrates attacking BPF programs that might be used for network security. So in Kubernetes, if you're using Cilium, to do the networking behind the scenes of the pods, this is kind of the same design. If you're using Istio to do service mesh security and control, then this uses some of these same techniques, but this demonstration uses a simple firewall. So in the top window, we'll start the firewall in a moment. On the right-hand side, again, we're showing Invary continually monitoring the system. On the left-hand side, we have a simple web server running on this machine, representing some maybe an intranet or an API server. We're also showing the dmessage system log down here. And the difference is that the attacker kind of has two little windows over here. So first, I'll just demonstrate from a remote machine that without this firewall running, that the web server is accessible. Now, it shouldn't be this way. I just wanted to show you what would happen here. So we'll go ahead and start the firewall. And again, this is a firewall written using eBPF traffic control programs. So that's the Shed CLS programs. And if you take a look at the running BPF programs, you'll see that these packet classifiers are attached inside the Linux network stack, specifically to the interface running on this box. And right now, the firewall has two different rules in place. One prevents ingress to port 8000, and one prevents egress from port 443. Again, just a simple example. So to attack this kind of, first off, with the firewall in place, that port is for the intranet web server is properly secured. And you'll see that packets are blocked when we try to fetch, when we try to get data off of it. But again, if the attacker wants to be able to get into the system from an external system, and they can temporarily escalate privileges, they can execute a different kind of attack, but this one is specifically against the ingress packet filter. So with that in place, it has, again, rewritten the instructions that are running down in the Linux kernel's networking stack. put there by this BPF program. And instead of not relaying information back to user space, which is how the EDR attack works, this works by looking at the packets and saying, I'm going to go ahead and allow this rather than drop this packet. So it's manipulating the packet filtering capabilities. So now the firewall itself should again allow one to get ingress to the port and to access this server remotely. That's why we have the log here, that we saw no packets blocked. But while this is happening, Invary detected again that a different BPF program lacks integrity. This time it's the ingress packet scheduler. And again, it tells you the hash of what was changed. And so this has some similarities to the previous demo, but it's showing that these same sorts of techniques work on different types of BPF programs that are used for different types of functionality, from software-defined networking to observability and security.
Steve, sorry to interrupt you really quick, but just a quick question that, I know I found myself asking, and maybe some of our viewers are too, but like, so that attack that you just carried out, like, did modifying the memory affect the actual firewall rules or other configurations?
No, so the firewall, the user space firewall application that's showing the statistics and the information log here is still running. It still has the same rules defined. The BPF programs that back this firewall application, ingress and egress programs, are both still loaded. They both still have, the kernel still reports them as the same number of bytes with the same internal kernel ID. So from the point of view of any monitoring software, either the firewall's own anti-tamper rules or any network monitoring or security monitoring, nothing's happening. The firewall's happy and continuing to perform as it is intended to, but obviously it's not.
Yeah. So I think a really great example of just like how some of the more traditional configuration change detection capabilities, like it's just interesting that it's a direct memory modification, and really nothing is going to detect this traditionally, right?
Yep. Yeah, it's just really, really difficult to monitor memory at runtime. That's a core capability of Invary's solution. And again, once the attacker is done, again, this should be able to be restored, and you'll see that it replaced the original instructions. They put them back in place in memory at the same segment. And so it's no longer modified, and in theory here, yeah, it continues to block packets. So, and also Invary now recognizes that the running eBPF program matches what was initially loaded and verified. Any questions?
I have some general questions that have come up while we were going through. And also for those attending, feel free to drop your questions in the Q&A if you have additional ones as well. In general, one of the questions that came up was, let's say I'm using LSM, using kernel lockdown. Does that matter for the demonstrations that we just saw?
So it depends on what your Linux security module is set up to do. They can be configured in different ways. You could potentially have an LSM that would prevent loading of new BPF programs, etc. But if the attacker can escalate privileges, there is probably a tactic that they can use once they've done that to be able to directly manipulate kernel memory, at least temporarily enough to, for long enough to run these sorts of exploits against BPF programs. Of course, they can also, in theory, do that with other parts of kernel memory too, which is why our base solution protects that. So it's unlikely. You can narrow down the paths by which an attacker might be able to do this by using an LSM or by using an EDR that does real-time security enforcement directly on the system using LSM. But yeah.
Yeah, but in general, just like we talk about this a lot at the kernel level too, read-only file system, kernel lockdown, IMA, turns out at runtime and memory, that stuff stops mattering as much. You should do those things. Those things are critically important to the security of your system,
Yeah.
especially as things come up and you have that trusted state. But extending that into memory requires, an Invary-like solution to do that.
Yep.
This one is sort of similar to some observability functionality we have, but does Invary provide visibility into hidden or unauthorized eBPF programs? In general, though, we didn't talk much about our observability piece and being able to say what's what, who's doing what, are they doing things that are maybe a debugging technique that they shouldn't. So do you want to expand on that, Steve, and talk about the other side, pass integrity, and how we're looking at the subsystem itself?
Sure. So in order to do integrity, our solution has to monitor all interactions with the eBPF subsystem to load programs, attach them, etc. So it's constantly watching that portion of the kernel for activity in and around BPF. And when it sees a program being loaded, it does a whole bunch of different checks. It lets you know by recording the process, the user, both on the user space side that ended up triggering the load of the program. It lets you know, what the program's. It shows you the hash of the raw instructions loaded out of the object or ELF file. It shows you the hash of those translated instructions after they've been through the relocations that are performed by libbpf while loading it. It shows you the hash of the JITted instructions. So it gives you a huge amount of information about what this program is, who loaded it, when it was loaded, and what it looked like as it went through the loading process. It even can decompile the eBPF program in memory and tell you what BPF helper functions or kfuncs are being used. Again, lets you know more about what's running on your system. And all of that capability is required in order to do the integrity check too. So we output that to a kind of log file that lets you inspect the activity.
And we should mention, if you want to learn more, info@invary.com, invary.com, easy way to get a hold of us. Lots of places on our website and other places to find this too. Last one I have. I'm sorry, Scott, go ahead.
Oh, go ahead. I was just going to mention too, I think it's just important to, think about these, things that we're talking about and what we've seen. Like, these aren't theoretical, right? We didn't create this just to say, hey, this is possible to do. Like, these are things that have actually been seen happening, right? There's eBPF kit, bad BPF, triple cross. There are known attacks that have used eBPF as the attack mechanism to compromise system and essentially again hide the activity that's actually going on.
Yeah, and you can understand why you see this active in the space all the time, just because of the power that the subsystem has, but B, the functionality that people are driving into it. I'm managing network traffic. That's a great place for an attacker to be at the end of the day. So absolutely, unfortunately, see this all too often in the model. Maybe the last question that came up was, I think we covered this, but just to maybe dive back in, what kind of attacks can happen against eBPF? So malicious program injection, privilege escalation, runtime. I think we covered runtime tampering quite a bit here. But I think those other attack vectors are as true, and even if we didn't showcase them. So you kind of do privilege escalation, Steve, using the eBPF space.
That's a difficult one. I think it depends on kind of how you define that. Generally, no, but once you have it, you can do things like disrupt EDR, disrupt observability platforms. You can manipulate sort of software-defined networking that happens as part of a service mesh or your Kubernetes cluster. You can open up, ways for malicious actors to reach into your network or to sort of stealthily exfiltrate data. There are proof of concept techniques that use like the XDP, super low level packet handling eBPF capability to stealthily exfiltrate large amounts of data over time in a way that can't really be monitored unless you do it externally at the network layer. So there are quite a large number of techniques that can be used once you can compromise eBPF.
Perfect. Another question just came in. So this one says, I'm assuming there would be an overhead in running Invary. Does it increase as the volume of eBPF programs increase, is maybe one way to say it. I would say in general, Steve, I'll let you take this in more detail. Between our kernel and eBPF memory measurement process, usually takes under a half a second to complete, and doesn't seem, we haven't noticed it scaling exponentially or sometimes at all based on volume of eBPF with a loaded system running a large EDR and something like Cilium and a few other things. We actually have customers experiencing that same environment. So we don't, the way we're actually measuring the memory is, I think, part of the reason that we're successful in not consuming the resources of the mission of that platform. But Steve, any additional thoughts on that?
Yeah, it's also tunable. So there you can trade off between the time it takes to create a measurement versus the resources, the compute time, the CPU, et cetera, needed to do that. It really is on the order of, tens to hundreds of milliseconds. If you give it more than one processor to do, it's quite fast. And the addition of, the additional load for each eBPF program that you have is really, it's microseconds and kilobytes of memory. So it is really quite scalable to do the integrity, eBPF integrity measurements.
And I would add too, if you're not as familiar with Invary, there's some optionality in there. We're measuring in the background on an interval, but that can be a minute, that can be 15 minutes, it can be an hour. A lot of that depends on the mission of the system. We also have the ability to do what we call a state transfer measurement. So something happens in the state of a machine. As an example, I have an HPC cluster that a job has just completed, and I'm going to check the integrity of everything kernel and eBPF layer before I run another job. I might also be running background checks, but there are, between the configuration of what you're measuring, how frequently, and the fact that we measure very efficiently, ends up really not being a problem. And I think the last piece of that puzzle is, most often we are appraising off the system that we're measuring. So the system that's measuring is just gathering that memory, organizing it, and shipping it off to be appraised by a separate system, so it's harder to tamper with, etc. There are times where we'll embed those two functions together, measure and appraise. Even so, it's still in the order of hundreds of milliseconds to do that. So it's a good question. Right. Any other questions from the attendees? Give it maybe 30 seconds. While we're waiting, just to mention, again, there's several more webinars on our website that go into kernel. There's one we did with panelists from industry and the NSA's Laboratory for Advanced Cyber Research on integrity measurement in general. That's a great one to go see and get their perspective on it and how you apply it to different realms, including the kernel and the eBPF layer. And then don't forget, I think end of September is what we're targeting. The next one where we're going to talk about the NSA CB open source project. We're going to talk and hear from folks that have done a wide array of analysis of the eBPF landscape, both people who are using it and then people who are securing it. So should be a great conversation. And I wasted enough time. There are no more questions. So I think that takes us to the end. So We appreciate everybody attending. If you have additional questions afterwards, don't hesitate to reach out. Again, info@invary.com. Jamie, any last words to close us out?
Nope, appreciate y'all. We'll follow up by email to make sure to close the loop. And thanks for everyone for attending today.
Thank you, guys.